Section 3-3, derivative functions. The objective, remember, of this section was given the equation of a function, graph the function and the derivative function, and calculate difference quotients. We're going to focus on calculating difference quotients here. We'll also go back and look at how we can sketch derivative functions given the sketch of a function. Let's start with this idea of a difference quotient. And there are actually three different difference quotients that we're going to talk about. The first one is what's called a forward difference quotient, which we will abbreviate as FDQ there. The term difference quotient, remember, is a term that we use to describe a derivative actually. It comes from the idea of the fact that you're taking a change in y over a change in x. So that change there is a difference in both the numerator and denominator. And you're dividing those two, so that's a quotient. So it's a quotient of differences, or a difference quotient, we call it. So let's take a look at what the forward difference quotient is. And I'm going to just sketch a function here that we can use to illustrate a forward difference quotient on. It really doesn't matter what our function looks like, but I'm going to sketch a function that looks kind of like this for each one of these three. And I'm just going to pick a point here. We'll call this x. And I'm going to go ahead and name that point there on my curve as the point x, f of x. Given the x value, we can plug that into our function corresponding y value. And then it's called the forward difference quotient. We're calculating slope. It's called the forward difference quotient because from this point x, I'm going to move forward some distance, and I'm going to go this distance h from that point. And that makes this point here x plus h. So I can name this point up here then as x plus h is the x value. F of x plus h is the corresponding y value. And then I can find the slope between those 2 points. That's what a difference quotient is. So let's label this as FDQ. And the forward difference quotient will be equal to, it's just rise over run, change in y's over change in x's. So it's f of x plus h minus f of x all over x plus h minus x. Change in y's over the change in x's. In fact, we can simplify that in the denominator. You can see that we have f of x plus h minus f of x in the numerator. But in the denominator, I've got x and I've got a minus x there, so those two cancel out to just leave me with just an h. There's my forward difference quotient. And actually, this is the difference quotient that we were using back in Chapter 1 when we were approximating instantaneous rates. It turned out that we were going to calculate an average rate on a smaller and smaller interval to give us the best approximation. And what we ended up doing there was picking some point x and then moving forward some distance to get to the next point, and then using those 2 points to find the slope between them. So actually we've done this before. We did this back in Chapter 1. We just didn't name it as a forward difference quotient. But there you go. Now if we have a forward difference quotient, you can probably guess what the next one is called here. And it is referred to as a backward difference quotient. We'll abbreviate that BDQ for short. And as its name implies there, you probably can guess exactly what we're going to do here. But let me sketch a function here again. It's going to look like the same function. We'll call this f of x. And I'm going to pick a point here, say somewhere around here. Let's say that we'll use. I'll go ahead and name that point as x, f of x, like we did to start off with before. But now, because we're talking about a backward difference quotient, now we're going to go backwards from that point. And we're going to go some distance h backwards from x. So now this is x minus h is the name of that point right there. And that corresponds to this point on my curve, which I'll name as x minus h, f of x minus h. And again, the difference quotient is just calculating the slope between those two. So let's go ahead and calculate that slope. Again, we're going to call this BDQ for short, backward difference quotient. And just calculate rise over run, change in y's over the change in x's. So it's f of x minus f of x minus h And that's all divided by x minus the x minus h. Now I put this in parentheses in the denominator so I don't lose the sign that needs to get distributed through those second set of parentheses there. Realize this will simplify again here. The numerator still stays as f of x minus f of x minus h. But now in the denominator I see that I have an x minus an x. So those cancel out. And that negative sign gets distributed through to the negative h. So it becomes a positive h there. So f of x minus f of x minus h all over h is our backward difference quotient. Okay, this one is, I guess, new for us. We have not done a calculation involving a backward difference quotient, but like I said, I think it makes sense that if we know what a forward difference quotient is, it'll probably only make sense then that we would have a backward difference quotient. All right, and that leads us to the third one, which the third one is what we call a symmetric difference quotient, which is kind of a combination of the previous two we'll see. We'll call this SDQ for short, for symmetric difference quotient. And again, we'll sketch a function here and use the same curve I've been working with just to illustrate this. And what I'm going to do this time is I'm going to pick some point x here, like I've done before, but because it's a symmetric difference quotient, what that means is I'm going to move forward from x some distance h, so we're going to come forward from there some distance h, and that will give us this point right here. We'll call x plus h. And of course I can name that point up here on my curve as x plus h, f of x plus h. And I'm also going to move backward from that point the same distance h. So this point right here, I guess to make it symmetric, it should be about right here, will be about x minus h. And so that corresponds to this point right here, which we'll call x minus h, f of x minus h. And again, the symmetric difference quotient is just finding slopes. So use your slope formula here. S dq is equal to change in y's over the change in x's. So it's f of x plus h minus f of x minus h. And it's all divided by the difference in my x's. So it's x plus h minus x minus h. So again, you'll notice that the denominator is going to simplify here. The numerator stays the same, so I'll just rewrite that, f of x plus h minus f of x minus h. But the denominator, I see that I have x minus x, so those will cancel out again every time the x's have canceled out. But this time I've got h minus a negative h. Don't forget to distribute that minus sign through those second set of parentheses down there. So h minus a negative h is actually h plus h, or that's 2h. So there is our symmetric difference quotient. Okay. A couple things to note here about this symmetric difference quotient, backward difference quotient, and forward difference quotient. Those three all use the same value h, and h we refer to as our tolerance. That's how small that interval is going to be that we're going to calculate the slope on. So we call that our tolerance. The smaller the tolerance, generally speaking, the better the approximation is going to be. All right, and the last thing to kind of relate it to what you saw in the first half of this section, we talked about this numerical derivative function called n-deriv. N-deriv is actually just a symmetric difference quotient with a default tolerance of 0.001. Now, of course, you can change that tolerance. We talked about that syntax there, so you can have it use any tolerance that you want. But by default, if you leave the tolerance as is, it's calculating actually just a symmetric difference quotient. So it's really nothing special there. It's just a quick way to calculate the slope on a really small interval on some function at a point. That's really all it's doing. That's why it's an approximation technique. It uses this exact same approximation technique we're talking about. All right, so let's take a look at an example and calculate some of these difference quotients here. This is on page 79 there in the book. They give you a function here, f of x is equal to x cubed, and they ask you to find all three difference quotients at x equals 2 with a tolerance of 0.01 is what they've done in their example, so we're going to do that. So let's start out with the forward difference quotient. I'll go ahead and do these in the order that we just discussed them. It really doesn't matter which order you put them in. You can do it anyway. But the forward difference quotient then, again, realize that we've got h is the 0.01, our x value is 2, and our function is x cubed here. So those are the key parts of this. But the calculation basically is going to be the same as the formulas we wrote down. I'm just going to replace the values in this formula with the values that were given. Since x is 2 and h is 0.01, that means it's f of x plus h. That's 2.01 minus f of x, which is 2. I'm just replacing our formula with the values of x and h that we know. And that was all divided by just h, 0.01. Okay? And we're just going to run that through the calculator. If you recall, back in Chapter 1, we did this over and over and over again, actually, many times. Let's see if I can make that so it's a little bit easier for you to see. All right. So in y1, what we're going to do is punch in your function, which is x cubed. And then just back to the home screen, I'm just going to have it calculate these difference quotients. So grab your y1 variable into your variables menu, VARS menu. So it's y1 evaluated at 2.01 minus y1 evaluated at 2. And we're going to divide that by 0.01. Again, hopefully that looks very familiar to you from what we did in Chapter 1. First two sections of Chapter 1, we were doing calculations just like this. So we get 12.0601. I'm going to go ahead and write down all those digits there. 12.0601. And the next one is the backward difference quotient, which is going to be f of 2, that's f of x, minus f of x minus h, that's f of 1.99, 2 minus the 0.01, all divided by 8, which is 0.01. We're just going to run that through the calculator, let it do its thing here. So it's at y1 at 2 minus y1 at 1.99 and divide by the 0.01, and we get 11.9401. 11.9401. There's our backward difference quotient. So you can see that just before this value of 2, we're calculating a slope of just slightly under 12. And after this value of 2, the forward difference quotient, it's a value just slightly greater than 12. And now let's calculate the symmetric difference quotient, that's dq, which is f of x plus h, that's the 2.01, minus f of x minus h, that's f of 1.99, divided by 2h, that's 0.02. We're just going to let the calculator crunch all that for us. We've got our equation, our formula written down basically. That's our work. And we're going to let the calculator do the work of crunching this for us. Just make a couple changes in our equation. And press enter. We get 12.0001. Okay. Now if you recall, we've actually done symmetric difference quotients when we were given a numerical representation for a function, a table of data. We took the interval that started just before the given x value and ended just after that given x value and used that as our best approximation. That's exactly what a symmetric difference quotient is. You've done this before. And if you recall, we even said that it turns out that the forward difference quotient and the backward difference quotient, that if you average those two, it gives you the symmetric difference quotient. We can just check that to see that in fact we do get that result. If I take the 12.0601 plus the 11.9401 and divide it by 2, the average of your forward and backward difference quotients turns out to be your symmetric difference quotient. Okay. The other thing I'll point out here too is the relationship to n deriv. We said that what we're calculating with a symmetric difference quotient is actually an n deriv or I should say n deriv is actually calculating a symmetric difference quotient is I guess the best way to say that. So if I take x cubed, my variable is x, and my value is at 2, and I have to put in a tolerance. The default tolerance would be 0.0001, but I want just 0.01 as my default tolerance, so I'm going to set that to a different value here, 0.01, and do the calculation there. You notice you get the same thing that we did for our symmetric difference quotient. So that will happen every single time. If you calculate a symmetric difference quotient, that's exactly what n deriv does. All right. Okay, that's the first part of this lecture here. The next part here deals with sketching derivative functions. And we talked about what a derivative function was in the first half of this section, that given a function, if you find the derivative at every single point, and then plot those points, and then sketch a curve through there, you get yourself a derivative function. The question now is, if I give you a sketch of a function, can you sketch for me what the derivative function would look like? And I want to go through the steps of how we do that and then go through a couple of examples here with you. So the first thing that we do is this. On our function f of x, we have to find out where f prime of x is equal to 0. That is, we need to find where the slope is 0. Those points will occur at the minimums. When you hit a minimum point, of course, your slope there becomes 0. When you hit a maximum point, your slope becomes 0. And also what we call plateaus. And plateaus are where your graph levels off and then continues on in the same direction it was headed before. So in other words, if you're increasing and then you level off to a slope of 0, but you continue increasing after that point, we call that a plateau. Okay? So the first thing to do is find where this thing has all those zeros at. Now, for the most part, to start out with, you're going to just look for mins and maxes on your function. Wherever you have the mins and maxes, you're going to get slopes of 0. But realize they can also occur at these plateaus. Now, the second step of this process, and we'll go through an example, actually a couple of examples using this in just a minute. But the second step is, once you've found all those points, is to plot a point on the x-axis at every such point there. Now, why do we plot a point on the x-axis? The reason is because we're trying to sketch what f prime looks like. And at all those points, f prime was equal to 0. So we need to plot a y value equal to 0, where y values of 0 occur right on your x-axis. So all of those points that we found give us x-intercepts. So we're going to plot all of those x-intercepts, in other words. Okay, those are the only places this function, this derivative function, is going to cross the x-axis, or at least touch the x-axis. It doesn't necessarily have to cross it, but it does have to touch it. Now, once we have those plotted, we need to just know what's happening in between these points. So we just need to remember our relationship between the rate of change of a function, the derivative, and the direction, whether it's increasing or decreasing. So here was the property we talked about way back in chapter 1, actually. We said that if f of x is increasing, then that meant that the derivative had to be positive. So if that's the case, if f of x is increasing, then we're going to sketch f prime above the x-axis. Now, why do we sketch it above the x-axis? Well, again, the derivative we're saying is positive. We want to plot then a positive y value. Where do positive y values lie? Well, they lie above the x-axis. Negative ones, of course, are below the x-axis. All right, that's if the function's increasing. The opposite then is true if the function is decreasing. That's the fourth step here. If f of x is decreasing, then sketch f prime of x below the x-axis. And again, that's because of the fact that f prime would be less than 0. If f prime is less than 0, I want to plot a y value that's less than 0. Y values that are less than 0 lie below the x-axis. And for most functions, we're going to find that this is enough information to give us a very good sketch, but sometimes we might need a little bit more help here. And so the last step of this process is to use the slope of f of x. Just look at the graph. In particular, look at where you might have horizontal asymptotes showing up. And you'll notice the slope is heading towards 0. That's one thing that usually is helpful. But you can also look at other points as well if you need them to help you get a good sketch of this function. but use the slope of f of x to help you sketch f prime where needed. Okay? Sometimes you might find out the graph doesn't have any mins or maxes, so it doesn't cross the x-axis at all. And so it might be a little bit difficult to get an accurate sketch of this thing without this extra step here. Okay, so think about where you might have slopes of 0 or approaching slopes of 0, I should say. Those are usually key points to look at. All right, let's try this out with an example. This is actually example 2 there in your book on page 80. And this one says the figure there shows the graph function f defined on the open interval from -4 to 6. And it says on a copy there, sketch the graph of the derivative function f prime and describe your process. Well, we really just went through and described the process already. So all we got to do is actually sketch the derivative of this thing. All right. So to do that, actually, let me make this graph just a little bit bigger here for us. So to do that, again, the first step was to find all of the zeros of this function. So I'm going to go through and find all the zeros and mark those. I'm going to do this in red here for us. So right here we have a minimum, and so if that's a 0 of my function, that means that the derivative function has to be touching the x-axis at that point. And I see that right here we hit a maximum. In other words, the slope right there, where we're going to sketch the tangent line to the graph at that point. The tangent line would be horizontal. So the slope there is 0, the derivative is 0, so I'm going to plot a point right here on my x-axis, and these points that I'm plotting are points that my derivative function is going to go through. And then finally I can see that right here I've got another minimum, and so the slope is 0 there as well. And so my derivative function has to have an x-intercept there as well. All right, now for the next part of this is the steps 3 and 4 really. Now consider what's happening in between these. So I can see that to start off with, on this little section of my curve here from this, it's not an endpoint here, but the starting point, that my function is decreasing. As I go from left to right, I'm heading downward. That tells me my function is decreasing, which tells me my derivative is less than 0. My derivative is negative. So I need to plot points that are below the x-axis. So I'm going to just pick some point here to start out with, and I'm going to say that I don't really know exactly how far below the x-axis I start, but this will be that point here that is undefined on my original function. It's not an endpoint, so I'm undefined there on my derivative function as well. And I know that I've got to be increasing in some way coming up to this 0. I start out negative, and as I get closer and closer to this minimum point, I get closer and closer to 0. So I'm going to just sketch some curve kind of coming up to that point. All right, and then as I go from that x-intercept to the next one, I can see that my function now is increasing. I'm headed upward. So I know that means then that my function, my derivative function has to be plotted above the x-axis. If my function's increasing, then I'm going to graph this above the x-axis. In fact, as I look at this, I can see that, I start out with slopes really close to 0, down here near x equals -3. They increase to some maximum slope somewhere, I would say somewhere around x equals -1. We get a maximum slope right there. But then they come back to a slope near 0 as they get closer and closer to this point at x equals 1 until finally at 1 we're back to a slope of 0. So that tells me as I sketch this thing that I have to hit a maximum slope somewhere around -1, somewhere around x equals -1. So it might come up something like this. And then it has to come back down to this slope of 0 at x equals 1, so it does something like this. Now, I don't know exactly how high for this thing to go. I'm guessing, or I'm approximating how high it might go right now. I could be close or I might be off. It doesn't really matter for right now. I just want to have a relative idea of what the sketch of this derivative would look like. All right, and now look at what's happening in the next interval. I can again see that I'm headed in a downward direction here, and my function is decreasing. So I know that I have to be below the x-axis, and again I can see that I start out with slopes near 0 here at x equals 1. They increase to a maximum negative slope here, somewhere around x equals 3 it looks like. and then start decreasing back towards this slope that's going to be 0 here at x equals 5. So that gives me an idea of what this thing should look like here. Again, I have a slope of 0 at x equals 1, and I have to decrease to some maximum slope here, somewhere around x equals 3 it looks like. We have a maximum negative slope, and then it has to increase back towards a slope of 0 as I get closer and closer to x equals 5 until finally at 5 I hit my x-intercept. And then finally, at the next interval here, I can see that my function is increasing. And so because of the fact that it's increasing, that tells me that my derivative is going to be above the x-axis. So I will sketch this last little chunk, something about like this. And that is going to be my approximation for what f prime of x looks like. Given f of x, there's a sketch, a possible sketch of f prime of x. Now there's actually several sketches that you can come up with here, because we don't have enough information or enough details at this point in time to know for sure exactly what this looks like. And what I mean by that is you may have decided that the sketch of this is better approximated with something like this. You might have said that I should start out my endpoint here at this value, and maybe it only does something like this as we come through here. That would be a correct answer. Okay? You've got the right x-intercepts. You've got this function above and below the x-axis in the right spots. That's a correct answer. Okay? Or you may have decided, you know what, I think this thing should have started further down. Maybe it should have started down here. And maybe as it comes up through here, it should have gone way up higher here and then come back down and so forth. You know, you could have made some claim as to why you think it looks like that, but again, that's correct in terms of you've got the right x-intercepts, you've got it above and below the x-axis in the right spots. That would be an accurate sketch of this a derivative. Okay. Now it turns out there's only going to be one sketch that's technically correct, but for right now we're not going to worry about that. Just get the rough sketch of what it looks like in there. That's what we're looking for. All right, let's take a look at one more example. And this last example says this. Now I'm going to give you a graph of f prime of x. And I'm going to ask you to sketch, first of all, f of x, and then secondly, f double prime of x. F double prime is called the second derivative. That is the derivative of the derivative. Okay? So I'm giving you f prime, and I'm going to ask you to sketch the derivative of it. Well, I'm going to actually start with f double prime here because that's the same process that we just talked about. So I'll go through that example here first. The first step of this, of course, is to find out where the zeros of this function, not the zeros of the function, where the derivative has zeros. That is where the max and mins are. So right here we have a maximum, so I'm going to mark that as a point. Here we have a minimum, so I'm going to mark that as a point on our x-axis. And now consider what your function is doing on these different intervals to determine whether your function is above or below the x-axis. So my function is increasing, I can see here. So because my function is increasing, that means my derivative must be positive. So I have to start out with a sketch of this above the x-axis. So it's going to do something like this, maybe. And then look on the next interval here. From between these two zeros, I can see my function is headed downward. It's decreasing. So I know that my derivative must be below the x-axis. So I'm going to sketch it below the x-axis, something like this. And again, you can see that it starts out with a slope of 0 here at this point. It's below the x-axis and ends with a slope of 0 at this point. So that's why I have to come back to that x-intercept. And then finally, on this last chunk of the function, I can see that it's increasing. The function's increasing, so therefore its derivative must be above the x-axis. The derivative is positive, so it must look something like this. This would be a good example then of what f double prime could look like. The derivative of f of x, f double prime. Okay? That's a quick review of the problem we just did, actually. Let's take a look at the next part of this one. The next part of this said to go in the other direction. What if I give you f prime and I ask you what does function f look like? Okay? A little bit more difficult, but we got to just think about the steps we just talked about, but do them in reverse. Okay? So the first thing that I got to remember is that when I started out with this previous examples, I wanted to find out where the maximums and minimums were because those told me the zeros of my derivative. So now when I look at this derivative function, I got to realize that where the zeros are on my derivative function, those indicate locations where I hit minimums or maximums or perhaps plateaus on my original function. So I'm just going to mark these with a dotted line. These are not asymptotes. I'm just marking them so that as I go through these points, I realize that I have to have a slope of 0 going through those values. All right. And then the next piece to consider is what's happening in between these zeros on f prime. And I can see that, for example, on this first section right here, that my function is below the x-axis. The derivative is below the x-axis. The fact that it's below the x-axis tells me my derivative was negative. And if my derivative is negative, then my function must have been decreasing. So I have to sketch a function, f of x, that's decreasing on this interval. So it's going to look something perhaps maybe like this. We'll have it level off right there. And remember, when you hit that dotted line, that's where we have to have a slope of 0. And now if I look on the next interval here, I can see on this chunk of the curve here that we're above the x-axis. F prime is above the x-axis. F prime is greater than 0. If the derivative is greater than 0, that means our function must have been increasing. So when I sketch my graph, I just have to have it increasing. So I'm going to just have it increasing. You can have it increasing as quickly as you want or as slowly as you want. Again, we don't know all the details of this function, but I have the general idea with this sketch. And again, I have to level off to a slope of 0 here at this next dotted line that I sketched in there. And now if you look at this next chunk, in this interval here, I can see that my function is below the x-axis. So since I'm below the x-axis, f prime must be less than 0. If f prime was less than 0, that means my function must have been decreasing. Let's make this thing decrease quite a bit here on this interval. Again, I don't know for sure how far it decreases at this point in time, but we're just going to sketch it so it decreases. Again, it has to level off to a slope of 0 right there, where f prime was 0. And now on the last chunk there, I can see that in this section of the curve that I'm above the x-axis. So if f prime is above the x-axis, f prime is greater than 0, that means my function must be increasing on that interval, so it must do something like this. There is a potential sketch of what f of x would look like. And you should be able to do that. Given a function, either f of x, sketch f prime, or, like we just did, given f prime, be able to sketch what function f of x looks like. And that is the end of this section here for us.